Hello. So this video will be the solution of the mass correction of a spring. Meaning, we have a spring whose mass is not zero. Say this is not zero. Then the question is, how does the frequency of this block depends on the mass of the spring. We know it depends on the spring constant. You may remember that when m is 0, if I don't have any, I can ignore spring's mass, then there is only one frequency. We'll just call it omega 0 square root of ks over m. So we can use this as a reference frequency and see how much that changes. So we can introduce some variables so it will help us understand things better, and have a variable epsilon, which is a mass of the spring over the mass of the block. So epsilon equal to 0 for this case, and omega 0 we'll just as a reference when mass is 0. So we can use these two symbols instead of some of the other symbols. So for instance, when we had an equation of motion, and this is 1 over v square, so this 1 over v square was shown to be equal to that, and that you can rewrite it in terms of epsilon omega naught and L. So we have this equation, the system here, system here. We can highlight it, system here, with a displacement at any position x given by psi of xt. So using this variable, we have an equation of motion which turns out to be this. The derivation is in the previous video, or the earlier part of this video. Okay, now in this system at x equal to 0, so this is the x-axis, and x equal to 0 lies here, and x equal to L is where the block is. So there's the boundary conditions. At x equal to 0, there is no displacement, so that's the fixed boundary condition. And x equal to L, we have block being pulled by force that's over here. And so this is the force on the block, and the mass times the acceleration of the block. So this will be the acceleration of the block, because the displacement there is the same as what's happening to the block. And you can write this again in terms of this variables omega naught square, which is a reference frequency for us. What are we looking for? Well, because this is a continuous mass distributed system, we're going to have an infinite number of normal modes. But we are looking for the lowest frequency of the lowest frequency normal mode, which is the lowest frequency normal mode. Okay, so how do I solve this? Well, so we will start with a solution of 1 subject to these two conditions. And since we are not interested in all general solution, we are only interested in frequency value, like eigenvalues. Then in that case, we'll say we started out at 0 velocity. Say we started out pull the block and it started out at 0 velocity. Then I don't need to have phase constant that goes with omega t. So we will have, the solution will look like psi of xt will look like a cosine some kx plus b sine kx. So this will give me where each part of the spring is, and times cosine omega t. So for zero velocity, I don't need a phase constant. For simplicity, it's not necessary. You can do that with another velocity, but it will not add to our understanding. Just be more algebra. Okay, so if this is my answer, and we have A, B, and omega unknown. You will say, hey, how about K? K is unknown too. No, actually, K would be, if you plug this in there, you find, so if you plug this in one, you'll find that K square times V square equals to omega square. So V square is omega naught square L square over epsilon. So given these guys, given the the parameters that we have, we know what V looks like, and so if we know K, we will know omega. So they're kind of related with each other, and because we just use the positive values, we can have a KV equals to omega. So we will use this to eliminate maybe K. So you could think of this as a, if you like, you can think of this as omega x over V plus B sine omega x over V, and the whole thing times cosine omega t. Okay, now to the boundary condition. So equation 2 means psi of 0 t is 0, means if this will be a times 1 plus b times 0 times cosine omega t is equal to a cosine omega t. That this is equal to 0 for all t. For all t. So this would mean a equal to 0. That means that this means I can simplify my original equation. So it will be simplify to psi of xt is just some constant sine omega v omega x over v times cosine omega t. Okay, so now we use in equation 3, and that's another boundary condition, the other boundary condition. So what do we get? If I take a 2 time derivatives, it's going to hit there and it's going to give minus omega square b sine, and I need to use x equal to L, so omega L over v, and then cosine omega t. On the left side. On the right side, I got minus omega naught square L, and so I take a derivative with respect to x, and I get omega over v, and I have a cosine omega L over v, cosine omega t. Of course, this omega t cancels out, and minus cancels out. Actually, it's a b here. B cancels out. So what do I? Let's see, what do I have? So I can get all the sine and cosine in one side and send the other guys on the other side. So it says the sine omega L over v over cosine omega L over V. Now other side is omega naught square L, and this omega square comes down here, cancels one of them, so I get omega naught square L over V times omega. Okay, let's see, this may simplify more. Omega L over V is equal to omega, and the V was omega naught L over square root of epsilon. No, this is another way. Okay, so let's see, the V is equal to omega naught L over epsilon. So this will be equal to omega L over omega naught L over square root of epsilon. So L cancels out. So you have a omega square root of epsilon over omega naught. So it's a nice in a ratio, you know, the frequency I'm going to get as a fraction of the frequency we expect. So that's this gonna, left side is going to simplify. How about the right side? Omega naught square L V omega. So I have omega naught square L, and V is omega naught L over square root of epsilon omega. So this also becomes very simple. This square root of epsilon omega naught over omega. So, but square root of epsilon in a different place here. So I'm going to do some multiplying and dividing. I'm going to say omega naught omega square root of epsilon I want. Then I need epsilon over there. So I can write this now using these guys as inputs. Tangent of omega square root of epsilon over omega naught equals to epsilon over omega square root of epsilon over omega naught. I write it because I want to show you how to solve equations like this. So if I solve this for a given epsilon, which is the ratio of the masses, and omega naught, which is Ks over capital M, so these are given, this is given, so I need to figure out what omega will satisfy this. If you plug into Mathematica or some other numerical solving program, you not get an answer. This is solved what is called graphical method. What do I mean? So I'm going to say let x equals to omega square root of epsilon over omega naught. So what we're trying to solve is tangent of x equals to epsilon over x. So say epsilon was 1. All right, that's the easy one, which meaning m is big M case. Well, what will happen? I will plot both of these guys versus x. So you know tangent of x is going to go like this, and then it's going to go like this. These are different branches of tangent of x, and then one epsilon is 1, so 1 over x or epsilon over x will go like this, and this is and omega is in the numerator, so the smallest x will correspond to smallest omega. So this is the x1 at which the two curves meet. So that's my solution point, and I'll show you that a program in which I solve this problem. Okay, so this is how you do it graphically. After that, I'll show you the solution, and then you will have a feel for it. So here is a let me see if I got the okay. So here is my program. This is in Python. I import NumPy and import matplotlib pyplot, and very simply I generate x between 0.1 and 1. I don't generate beginning 0 because 1 over x will give me a whole bunch of range, and then I'll have to work with restricting the range for the y values. I could do that, but I choose not to do it. And so I have a tangent I plot, and then I plot 1 over x, and then I show them in the same graph. Alright, so here is the point, which is, then you read it here, this is like 0.82 or 825, this is 0.9 is here, let's say 0.85. So when epsilon equal to 1, I get 0.85. So my answer is, so I got when epsilon equals to 1, I get x equals to 0.85. Well, what does x mean? X mean this, so omega will be omega naught x over square root of epsilon, and so this is my x1, so I'll get x1, so I get 0.85 omega naught, so 85%. The frequency has actually dropped to 85%. You can verify this, check if that's true, if you also get this. I'm going to stop this video now. I hope you learned a lot from this example. Take care.